Hi, I am Darlene Squibb, and I'm from Goddard's Environmental Management Office, and I'm sitting in for Dr. Trena Ferrell today, who is supporting headquarters, who usually does the introductions and the Q&A at the end. She usually has a long list of thank yous for the Earth Day schedule this month, but we really need to thank her for the schedule events that we've had this month. And there's 2 talks that will be next week. So our talk today is with Dr. Peter Jacobs, and from what I heard, newly minted doctor, who is part of the public affairs team in Earth Science Communications. Besides his physical research and better understanding past climate changes through climate models, he has also worked for the Center of Climate Change Communications. And he will talk today about how to better communicate your science. So over to Peter.
Hey, thank you. So thanks to Travis and Trena and Darlene for all of this wonderful Goddard Earth Month programming. There have been a lot of great speakers already, and I am very aware that everybody's time is precious, so I'll try to get through this stuff quickly to leave time for questions or just to get you all some time back at the end. Basically, the premise of the talk is exactly what Darlene just said. For many of us, the work that we're doing at NASA at Goddard is driven by evidence. That's true for the science folks and the engineers, but a lot of people all over center. Anybody in logistics, that kind of thing. But as much as our science is driven by evidence, something that you kind of notice, both inside and outside NASA, is that a lot of people who sort of do science, their science is driven by evidence, but how they communicate isn't necessarily. So I'd like to talk a little bit about that today, and in order to sort of practice what I preach, I'll be evidence-based here, and sort of give you the takeaway up front. So one of the things that we do on the science side is sort of do these long, winding buildups of background and context, and then get into the methods, and then finally at the very, very, very end, when you're rushing to finish, get to the sort of the punchline, the so what. And the best practices from communication are completely the opposite. You sort of start with a takeaway. And then once you've done that, you can sort of give the background and give the context. So, just to give you the too long, didn't read. Basically, when it comes to climate change, to be evidence-based, to get to the what, there's really only just 5 facts, 10 words that you need to remember. This is very, very easy. It's real. It's us. Experts agree, it's serious, and there's hope. That really is what people are interested in when it comes to climate change. And basically, if you know how people think about those 5 things, you'll understand almost everything that they think about climate, both as a science issue and sort of a public and policy issue. And in terms of sort of how to get that information across, the how is also super simple. Basically, simple, clear messages, repeated often, delivered often by a variety of trusted sources. That's pretty much it. So if you want to log off now and go spend the rest of your time outside having a nice lunch, that's the takeaway. But if you want to hang around for more, I can do a little bit of a deeper dive. But 5 key facts, 10 words, and simple, clear messages delivered often by a variety of trusted sources. How I got sort of into this area is a little bit of a sort of a shaggy dog story, but I'll just go through it, fairly quickly. Like a lot of people probably who work at NASA, I was super into, kind of sci-fi as a kid, alien creatures, alien worlds. And, at some point, it sort of clicked with me that, while, that stuff is science fiction, there really were these sort of alien things about Earth, just from times long in the past. This wasn't something I realized as a kid. This was something it sort of didn't click for me until I was an adult. I'm sure I had a dinosaur phase as a kid, but I don't really remember it. But this sort of stuff, like with pterosaurs that were as tall as giraffes, it just kind of blew my mind that this was, something that was happening on the same planet that we live on now, just further back in time. And I really sort of couldn't help but wonder how we knew about this stuff. And the how we know about this stuff wasn't just, sort of what did these things look like? I was familiar, I think, just through cultural osmosis that, they're paleontological digs, like that's how we know what the bones look like. To a certain extent, that's how we know, what the actual creatures look like. But more sort of interested in, what was the environment like when these things were alive? How alien really did the planet get in the past? And so just basically just understanding, what the world was like when it was really different, what the environment was like millions of years ago. So I started doing grad school for, this sort of thing, and it's an entire field on its own. It's kind of called Paleoclimate, which just means climate of the past. This is me doing field work out in Virginia, where I'm obviously standing on the ground, but that part of Virginia was underwater about 3-4 million years ago. During a time called the Pliocene. There's little white things in the cliff that I'm standing next to. Those white things are giant scallops because, that was essentially an ancient sea back then. And the sea level was higher because it was warmer, and it was warmer because CO2 was higher. And that is why we study the Pliocene in part, to kind of understand how the future will look as things warm up. And you can see in the picture I had probably the most important job on the fieldwork team, which was just holding the backpack. What I learned very quickly, sort of getting into grad school for paleoclimate, was that within the scientific community, there was essentially no confusion or debate or discussion about was climate change real and caused by humans. That was not something people argued about. It was just what the science showed. And in fact, most climate scientists were completely uninterested in kind of going over that again and again and again, and moved on to other more nuanced topics, things that we were less certain about, sort of trying to constrain uncertainties, get into the nitty gritty, move beyond those basic questions. The science had moved on. And that made me really confused. I was coming in, as I said, this was not like sort of a lifelong passion of mine. I was coming into it as an adult already. I did not understand if the scientific community was so certain about this stuff already, why was it such a debate, in the public? And I really, like probably a lot of people, I was, on social media seeing people sort of argue about this stuff. And I would argue back, it didn't really make sense to me, this giant disconnect. And so basically at that point, I sort of was on two parallel tracks, and one of those was just sort of continuing on with the physical science stuff, just the climate of the past and how that's going to help us understand the future. I also was doing some work on like how ocean heat drives increased rainfall from hurricanes as we're heating up the planet. But I was also sort of interested in, how the public understands science and why, if science says something, why the public doesn't just sort of immediately get it, or, if people have sort of a misconception and you say, hey, that's not actually right. Here's what the evidence shows. That this isn't actually how the world works. People don't just say, oh, great, thank you. And I discovered that there was this entire field basically studying the science of how we communicate science, how people accept things or reject them, all of that stuff. And that was really an eye-opener. And one of the main groups that does that is called the Center for Climate Change Communication. It was actually at the same university that I was doing this paleoclimate stuff at. So right in my own backyard. I did not know this stuff existed. They had these amazing and, at the time, kind of seemingly magical tools. Like if they wanted to know what people thought, they would just ask people what they thought. They would poll them. They would survey them. To me, kind of studying the physical science side, it was like a giant revelation. So they have been doing these studies of public opinion about climate change, for more than a decade. They also used these very, to me, exotic tools like audience segmentation, which is basically just understanding that the public isn't one giant entity. It's really just a bunch of different audiences that all have their own shared belief. They're not one giant audience. They're sort of a multitude of audiences. And this was just like mind-blowing. It was absolutely amazing to me. I decided sort of then and there to try to get involved. This is where I sort of found out about these 5 key facts. That's pulling straight from the work that the Center for Climate Change Communication does in conjunction with Yale. So I did a graduate research assistantship with them. It probably slowed me down in actually finishing my degree, but I felt like I had to get in on this. I've since come to NASA. I don't work with these folks anymore, but they're still working with us. They're still working with NASA, and they've recently released a survey about public, attitudes and information on what the public kind of hopes to get from NASA on climate change. And that's sort of the focal point that I'll use to talk about some of this stuff. This is specifically referring to a survey that looked at people's sort of mental frameworks and beliefs before and after visiting the climate site from NASA. And their top line findings, they've kind of bucketed in a way that matches up very much with those 5 key facts. And that's not sort of by coincidence. Those 5 key facts were sort of they were a result from repeated surveys from the public. So surveying the public and wanting to know what the public thinks about this stuff leads to these 5 key facts being important, then asking them sort of what they're hoping to get from NASA. The fact that maps to those 5 key facts is, that makes sense. I'll start with the one at the bottom, which is basically just saying, it's about 11%, rounded up to 18% when you sort of bucket some miscellaneous related questions in, which is basically saying, what do you understand or work on? What do you do? And this really falls into the sort of the how. We are a trusted source. We're a tremendously trusted source by the public. When you ask the public, who do you trust for information about climate change, far and away, the public is super interested in what agencies that do science like NASA think, and what they're working on. So, a great thing to keep in mind is to have an answer for people when they want to know what you personally work on that does not downplay your work. A lot of people, when they get asked this question, they go very self-deprecating. They refer to the work that they do as maybe not as interesting as some of the work that their friends do, that kind of thing. They sometimes we get, our best scientists still have a little bit of imposter syndrome where, they don't want to sort of take ownership of their successes, but have an answer for when people ask, what do you work on? That is something you can explain to people who don't know the first thing about what you work on, what your day-to-day is. And that is them sort of communicating to you that you're a trusted source. They want to hear it from you. To go to sort of the top line finding, the sort of the number one bucket of responses that this survey found people were really interested in was, solutions. And that pairs directly with the last key fact of the 5 key facts, which is that there's hope. People are more than ever, this is based on repeated surveys over time, desperate, hungry for information about hope. When you tell people that it's serious, when you tell them the scope of the problem, but you don't pair that with the knowledge that there is still time to do positive work, people get really disengaged. They get demotivated. They tune out. They say, oh, well, it's too late. I just don't care anymore. And this is something that we have not done a great job talking about at NASA, I would say until fairly recently, in part because there's a fear of getting involved with policy, and there are very good reasons why, NASA is sort of policy agnostic. We're policy relevant. We don't prescribe policy. We also, we're not selling Teslas, that kind of thing. But, our work is directly relevant to solutions. There are real world work is being done to plan solar power, wind power, that's using the science that we do. It's using the science that we do specifically here at Goddard. Our atmospheric modeling folks at GMAO who make the MERA reanalysis product, that is used around the world by people trying to understand where to put solar panels and get the best bang for their buck, where to put wind turbines to get the most bang for their buck. So I feel like, understanding NASA's role, even though we're not telling people what to do, we are part of the solution story, and it's great to have that information. Another just kind of communications 101 thing is to focus on what's known, not what's unknown. Even though what's unknown is really the bread and butter of science, that's the stuff that's most interesting. I mentioned, when I first got into science, people were really not debating the question of were humans causing climate change anymore. They were much more interested in more nuanced topics, like the human role in extreme events and, sort of kind of trying to understand how we could narrow down things that were going to happen in the future. But to the public, these sort of basic fundamental things that maybe the scientific field has moved on from, they don't necessarily know that. People really are desperate to hear, how do we know humans are causing climate change? Huge, if you add these up, it's, about a third of the responses to this survey were about either, is climate change really happening and how do we know it's caused by humans? So I'll bucket these two together just in the interests of time. How do we know that climate change is really happening? How do we know that humans are causing it? How do we know that climate change is happening? That, something directly that we do at NASA, our colleagues at GISS, which is part of Goddard, have arguably the best surface temperature data record of any organization. And I say that with no slight intended to our colleagues at NOAA or the Met Office, but sort of in my mind, the record of records about is the planet warming comes from NASA. It takes information from weather stations across the world going back more than 100 years and does a ton of analysis to sort of clean up errors in the data to kind of match it together in time so that it's one continuous record, and that shows us that the planet is warming. And it's not just that we see this warming in sort of the surface thermometer record. Ice is melting around the world. So these are graphs of Antarctica losing ice and Greenland losing ice. And this data comes from NASA, and it comes from stuff that Goddard has worked on from GRACE and GRACE follow-on, where basically there are these really cool, there's a pair of satellites that's moving around the Earth, and gravity sort of is tugging on these satellites. And we can measure the mass of objects on Earth, like ice sheets, based on how much gravity is pulling on them. And we can use that to see how much ice is melting. And the ice is melting because it's getting warmer. So even if we didn't have a record from instruments showing temperatures rising from thermometers, we would still be able to look around the world and see ice is melting. The air is able to hold more moisture because it's hotter. Seasons are sort of changing for plants. They're blooming earlier. They're able to grow further northward, that kind of thing. So the natural world is giving us a million different reasons to know climate change is happening. When we talk about how we know that humans are causing climate change, I think a lot of times we just sort of say, well, greenhouse gases are going up and temperatures are going up, and we just leave it there. And that, I think, to a lot of people, we take it on the inside for granted because there's a physical reason why greenhouse gases go up, and that means temperature should go up. So it's basically just physics. The physics of greenhouse gases being greenhouse gases, sort of absorbing and then radiating back infrared energy is essentially, it's the same technology that heat-seeking missiles in the military are based on, or those little thermometer kind of gun things that you can just get a temperature. It's fundamental physics. And so we just kind of leave it as, well, the greenhouse gases are going up, that's because of us, and temperature is going up. So that's it. That's how we know. But to a lot of people who don't sort of understand the physical science behind it, they just see us kind of saying, well, two things are happening at the same time, and that means that there's a cause there. And a lot of people, I think, have experience with, knowing that just because two things are happening at the same time, that doesn't mean that one is causing the other. So I genuinely feel like we can be better, when we talk to the public about that. We have the ability to be much more direct about how we know that humans are causing climate change. And one of the ways that I like to talk about this is sort of fingerprints. There are fingerprints that we expect from human-driven climate change, and there are different fingerprints that we would expect from natural climate change. So this is a paper from a long time ago, and it was done by our colleagues at GISS. This is a little bit hard to decipher of a graph, but basically what it's showing is sort of the latitude across the bottom and sort of elevation from the ground up into the atmosphere going upwards. And on the left-hand side is what happens if you were to increase energy from the sun. And on the right-hand side, it's what would happen if you sort of change the amount of energy in the climate by roughly the same amount as you were doing with the sun, but by increasing greenhouse gases. And the big difference is at the very, very, very top of both of these graphs, there's cooling in the increased greenhouse gas scenario. And the paper basically just says, really, if you were going to warm up the planet by making the sun hotter or by increasing greenhouse gases, the only difference between what that would look like, the surface would warm in both cases and the lower atmosphere would warm in both cases. But when you increase greenhouse gases, it actually causes the stratosphere to cool. And it does not happen with increased solar energy. That warms everything up. And so then this is a more modern version of a climate model, also from GISS, showing basically the same thing, but I think it's a little easier to see. On the left, you see what happens when you make the sun a little bit warmer, and on the right, you see what happens when you increase CO2. And really, the big difference between those two is you see this purple and blue stuff happening at the very top of the panel on the right, and that's that stratospheric cooling. That is something that cannot happen if something else, like the sun, were warming the climate. It's something that specifically happens when you increase greenhouse gases. It's a fingerprint of climate change. And what you're seeing on the left is sort of the temperature throughout the stratosphere, from the upper stratosphere down to the lower stratosphere, where the black line is the observations that we have, and the colored lines are what climate models think should be happening. And so there's this fundamental prediction that goes back 50, 60 years, long before we had these records of what the stratosphere was actually doing. And it's a prediction that was made, completely before these observations existed. It's very counterintuitive that it should be happening, but it's exactly what we're seeing. It is a fingerprint of humans causing climate change. And, the way to think about climate change is really to think about, the Earth has sort of a balance, like your bank account balance. Like there's energy that comes in, there's energy that goes out. It's like what the money that's coming in versus the money that you're spending. And what we're essentially doing with climate change is we're changing that balance. We're changing when we have energy that's coming in from the sun, that hits the Earth. Some of it gets scattered before it makes it down. Some of it makes it down, gets absorbed by the Earth. Once it gets absorbed by the Earth, it gets radiated back out at a different wavelength. That then tries to leave the Earth to balance out the energy coming in with the energy going out. But greenhouse gases stop that second part of it. They reduce the amount of the long wave radiation that should be escaping back out to space. And basically what that means is that you're building up heat. You're building up heat in the system. And where that heat goes, we actually can track. The vast majority of it goes into the oceans. This is sort of an account of where all of the heat is going. You can actually see, if you look, like the actual amount of heat that goes into the atmosphere and the land, which are purple and sort of the off-putting colored brown respectively, is fairly small. The sort of the warming that's picked up by those surface thermometers is not really the major place where this heat is accumulating, which is really in the ocean. And what that tells us is that climate change isn't caused by natural cycles in sort of how the ocean behaves, because when the ocean warms the climate, it does that by releasing heat into the atmosphere. So during like an El Nino event, what's happening is ocean heat is going down slightly in the ocean and then going into the atmosphere and warming things up. And what you would expect to see if the oceans were responsible for climate change is basically your surface temperature going up, but the ocean heat content going down. And instead what we see is that the temperature has been going up and we're still building up enormous amounts of ocean heat content. So this is another just basic physics explanation of why we know that greenhouse gases are causing climate change. In terms of the experts agree, this is something that I got very interested in. This turns out to be a really, really important thing for public understanding of science, not just about climate change. It's a fundamental thing when you're trying to help people understand things about evolution through natural selection, when you're trying to get people to understand whether or not vaccines work, whether the shape of the earth, it doesn't matter. People want to know, what does the scientific community think? And we've already seen that the public trusts scientists on climate. I showed you this graph before. And this is just another way of looking at it, which is sort of geographically. The public trusts the scientific community on climate change, very, very broadly. So the public trusts scientists on climate change, and scientists agree that humans are causing climate change, and there's enormous scientific consensus on that. Then why is the public confused about climate change? And this is showing you, actually, do people think that climate change is caused by human activities? And you can see this is a much, much, much lower percentage of people than who trust scientists. So people trust scientists, scientists agree, but then people don't think that humans are causing warming. And that's because we missed a step, because the public is actually very confused about what scientists think is happening. The public perception of scientific consensus is just so much lower than the reality. And so some of the things that I worked on before I came to NASA were about sort of communicating this consensus to the public. And we tried to pursue a strategy that I think is a good model of any sort of science communication, which is really pairing, good research, published in a good journal, but then also getting that information out to the public. So we had a paper in 2013 that was sort of quantifying the consensus on global warming. It was, well received, I guess, in the scientific community. There were some people who said it was a little like, what's the point? Because we know that, all of us climate scientists already know that. But it's gone on to be very cited, and it was a fun thing to work on. But we really weren't necessarily trying to get this information to the scientific community, because we already knew the scientific community knew this. That's why the consensus is so high already. What we were really interested in was sort of the public dissemination of this. But we knew that the credibility of that really also turned on having the actual the research on it. So we basically looked through a giant database of scientific abstracts, found ones that mentioned climate change. Then of those, this is tens of thousands of them. Of those that mentioned climate change, did they take a position about whether climate change was caused by humans or not? And then if so, was it yes, was it no? And then we followed that up by actually contacting the authors and asking them about their research as well. So we kind of did it in a two-pronged approach. And then we tried to get it out to the public, and we did fairly well. We got some traditional press about it. We also got some sort of, some social media stuff. There were some influencers from YouTube and Twitter. Like there's a guy named John Oliver who is big on YouTube. He also has a show on HBO called Last Week Tonight. He covered it, which was great to see our paper there. Then there was a like a Twitter power user who covered it. His name is Barack. And that gave us a big boost. So, that combination of peer-reviewed research and, getting it out to the public in a big way really made a difference. And that was a super successful strategy for us in terms of that. So I was hoping to leave a lot of time for questions. I'm gonna wrap it up here. And then if we can have a conversation about it, great. And if you guys just want to go live your lives, that's also cool.
Hello, great job, Dr. Jacobs. Phenomenal. Kudos. I'm glad I got to join. Sorry that I'm a little late. I just got finished with the headquarters Earth Day event. But hello, everyone.
I love your background. Can you tell people what your background is if they don't know what it is?
Yeah, it's the Earth Day. Every year they do an Earth Day poster, and this is the image. And you can actually download the image this year, since we're not printing out the hard copies. So thank you. So I'm not sure, are there any questions? I don't see any questions in the chat box, but you want to unmute your mics? Or chat. Okay, great. All right, so here we go. Okay. Somebody's asking, in a nutshell, what do you think NASA's overall communication strategy should be with regard to climate? Good question.
I think that's a very profound question. We have sort of a responsibility as a government agency that is, maybe different than if we were, a nonprofit or something else. What we want to do is, number one, we want to tell people what we're doing. That's sort of a mandate that we have. We're required by law to sort of tell the public. We're required by law to study the Earth. We're required by law to communicate those results. I think what we would hope to do is not just sort of do that because we have to, but do that because we recognize the value in that. I mentioned before, we're supposed to be sort of policy agnostic. We're not supposed to tell people what to do with this information, but certainly what we want to do is make sure that people know everything that we know in order to make the best decisions that they can. I think we, as an agency, are very, very much, and Trena probably knows this, I know a lot of people in the communications world know this, we're really trying to get our arms around, climate as a portfolio of work on the science side, as a portfolio of work on the comm side. The reality about NASA is that, we're an agency, and that kind of maybe implies a very top-down approach, but we're really a bottom-up, kind of science organization where our scientists compete for grants or, projects. There are pockets of scientists working on very similar things who don't work together. And that's wonderful. That really breeds innovation. Getting people to look at the same questions in different ways is actually tremendously, tremendously important in science. But that then does lead to situations in which, we've got a million different people communicating about climate in a million different ways. And while there is great value in doing that, in some respects, there is also a lot of value in narrowing down on those simple, clear messages and then repeating them often and repeating them through a variety of channels. So instead of repeating a bunch of different messages from a bunch of different channels, also be consistently repeating some of those messages. And I think we can do better on that.
Thank you. Next question. Because of the psychological effect that you described, where you can't really change someone's mind with evidence, what do you think is the cause of the generational change in approach to / acknowledgement of climate change? And do you think that's a good opportunity to target a receptive audience?
Yeah, I think it's worth sort of, not overly committing to this idea that you can't change people's minds. You can change people's minds. That is something that can happen. It takes a lot of time. It takes a lot of work. And really what it takes more than anything else is trust. And it's just, to kind of to back up a step, and why does this happen? And why does this happen about certain topics more than other topics? Really what usually is going on when you get this very big divergence between, the public understanding of a scientific topic and the science itself, or the scientists' understanding of that same topic, is that there's some sort of identity conflict where something about the way a person thinks of themselves, or maybe even more specifically, thinks of themselves as part of a group, is conflicting with the information the scientific community has, or they're insulated from that information and don't really have access to it, or think it's more uncertain than it is. So it is possible to get through to people, but you have to be trusted. And that can take a variety of forms. You can develop personal trust with people. Doing that in a single interview is going to be really hard. Doing it at an outreach event is going to be hard. But what you can do is you can talk to people in your own lives. What we find is that a lot of people, even scientists, don't talk about climate change. They don't talk about climate change to their neighbors and friends and family. People assume that people will respond more negatively to that kind of conversation than what we find even sort of skeptical people actually do. So people are sort of self-censoring in their personal lives when they could be a trusted source. What explains the generational gap? I mean, I think, having sort of lived most of your adult life with sort of a mental model of, gosh, this is tricky. I don't know how I can say this audience appropriately for NASA. There is a strong ideological component to the rejection of climate science, and that ideological component, maps very well to political ideology and political partisanship on one side of the political aisle, and it also appears to be sort of very tied into a belief that industry and economic growth are like basically a sort of a force for good, and that regulatory action impedes that and is bad. And so, those beliefs are more prominently held in older generations than younger generations, and that does quite a bit of the work to explain the differences in the generations. But there's also, people who are young have lived their whole lives, I think, experiencing information about the consensus on climate change in a way that people who are older have not. And one of the things that we've learned through the social science side of this is that understanding how much scientists agree is a gateway, fact for people. When even people who are ideologically predisposed to reject the finding that humans are causing climate change, if they think the scientific community accepts it, then they accept it, because most people think of themselves as being pro-science. So I hope that answered the question.
Thank you. I've heard that mentioning the percentage of scientists who agree is problematic because it makes people wonder, what about the 3% who disagree? What are your thoughts?
I think that's a great question, and there is actually research on this. The research kind of gets about it in a few different directions, but I'll try to explain this, I think, as straightforwardly as possible. That would be actually hypothetically true if people assumed, if you walk in the door, and you can do this by don't look at climate change, look at a different topic. So this is actually an experiment that's been done where you just make up a topic. You say there's like a lake, and that lake is being polluted by a certain chemical. If you just kind of get people, because this is a hypothetical situation that's not actually a real world situation, most people will just assume that there's scientific agreement about a topic. So their mental model will be like, oh, you're telling me there's this problem. Scientists must agree that there's this problem. The consensus is probably 100%. If you tell them then that like the scientific consensus is like 80%, but you still tell them the facts. This chemical is causing this pollution and 80% of scientists agree. They're like, wow, 20% disagree? Well, then maybe all of a sudden they're not so sure. And so their belief that the problem is actually happening goes down, even though you never told them there's any doubt about the facts. You've reported the facts as facts. You've just told them the percentage of consensus was lower. So that, I think, is what the person asking the question is getting at. Why that's different about climate change, and why this is a great question, is because people's mental model of the level of consensus on climate change is terrible. It's already terrible. They don't think it's 100% agreement. They think it's like 50% or 40%, or even lower. So when you tell them that it's 97%, and by now, our research was several years ago, it could be higher than that now. But if you tell them it's much higher, even if it's not 100%, what you end up doing is increasing their perceived level of scientific agreement, and therefore improving all of those other key beliefs, if that makes sense. So it's a great question. The answer is people's pre-existing mental model is way lower, so you're boosting it.
Thank you. Someone said, great talk. I totally agree. I heard you talk about this topic earlier, and that's why I thought we should bring it back again so the majority of the people could hear it. So someone's wondering, how can Goddard communications teams for non-Earth science missions best support amplify the climate change messaging?
I think that's a wonderful question. I mean, I think one of the most favorite, best things about working in the Office of Communications at Goddard is being able to do stuff that's a little bit outside whatever you're assigned to do, whether that's sort of volunteering at outreach events or, working on live shots when you have to volunteer, for somebody else's big important mission. I mean, because climate change sort of affects everything. If you're involved with heliophysics, the relationship between the sun and the earth is a very natural starting point. If you're involved with, astrophysics, our searches, and this is also true for planetary science, when we're deciding about where to land on Mars or what the Martian climate looked like a long time ago, or we're looking for planets in other solar systems, a lot of our understanding of that stuff is based on what we know about Earth and about, things that I talked about, like the energy balance of a planet. That's what ultimately sets their climate. So I would say there's not like a super one-size-fits-all answer, but looking for those connection points and then developing messaging about how to work that stuff in is a great start.
Thank you. Is there a straightforward physical explanation for the cooling of the stratosphere?
There is not a straightforward explanation. There is an explanation. This is one of those things where, like I was saying, this was discovered like 50, 60 years ago, way before it was ever something we could actually observe. The people who actually wrote the first papers showing this when they were asked about this, they would kind of mumble and then go past it because it's so complicated. But really, the short version is like there is an energy balance of the stratosphere as well as the planet as a whole. And basically, the temperature of the stratosphere is set by how much energy it's receiving and how much energy it's sending back above itself. And basically, you're essentially starving the stratosphere of energy it would be otherwise receiving when you're increasing the CO2 in the troposphere below it. So there's a great analogy about sort of insulating a house and how that affects the temperature of the outside surface of the house. But I feel like even that, it's like a hugely involved metaphor. So basically, you're kind of starving the stratosphere of energy from below, even as it's emitting from above, if that makes sense.
Great. Someone's wondering if you can send me, and I guess they can email me, I'll give it to them, the link to the review paper that you showed.
Yeah, I mean, if it's the consensus paper, we did an update since then, but yeah, I can send links to all of them.
Great, thank you. In your opinion, what are the best things that we can do to break through the noise and communicate scientific consensus on these controversial topics?
I mean, if that's a question about what we can do as NASA, I think, I think making sure that our own people, whether they're communicators or whether they're scientists, are aware of, in that question itself that you just read, it says controversial. These aren't controversial science issues. And we have people who self-censor because they think they're supposed to. They think, gosh, I don't want to tick anybody off. I shouldn't really talk about this stuff. But climate change is not considered a political topic by our legal office. It is not a political topic. It's a scientific topic. You talk about the science, talk about what we do know, focus on what is known, and just be clear about it. And if you're not sure because you don't feel comfortable with the facts yourself, reach out to somebody like me and we can, give you all of the papers that you would ever want to read, backing all of this stuff up. The National Climate Assessment does this sort of thing. The IPCC does this sort of thing internationally. The science is rock solid on this stuff. We should feel very comfortable talking about it.
Thank you. How is the intersection between the scientific community and the political community and mass media? They all seem to be telling different stories.
I agree with that. I think the political side of that is something that unfortunately we're a little boxed in about what we can do anything about. Certainly we work to get our information to the media in terms of the press. We can continue to do that. We have a wonderful, gigantic sort of built-in, audience out there, and we're reaching new audiences all the time about, our human exploration, our planetary science, our astrophysics. So I think just, we can keep pushing out what we do know, and we're already trusted.
Thanks so much. I want to thank everybody. The chat box is on fire. Someone's a comment, it would be helpful if NASA and NOAA would provide simple data, evidence-based data, so that's good.
Yeah, I mean, I just want to be really clear that, and I didn't get to this, I don't think, but, we do that, and so does NOAA. Our temperature calculation and the data underlying that, the code to produce that graph, everything, all of that stuff at GISS, you can download it yourself. You can run it on your own computer. You can even download the climate models that GISS uses. It obviously helps to be able to run those on a supercomputer, but you don't need to. And there are simple versions that run on a desktop. So in terms of the data availability side, NASA and NOAA and USGS and a lot of partners throughout the government are really good about having data available. It's not always super easy to find, but again, if you specifically are looking for something, I'm always happy to help.
Great. Another comment about another great presentation. Some of the most compelling evidence of climate change comes from long data records, one of NASA's strengths. However, most people react to the local/recent, not the distant/historic. What are your favorite climate fingerprints that meet that criteria? Good question.
Yeah, I mean, the length of record is super important. It's super important for sort of what we would call signal detection. So if you want to see a change in a data set over time, the longer your data set is, the easier it is to see a change in that. And so that really does, play into this idea of fingerprints. My go-to example for that is the stratospheric cooling, because that's such a stark, sort of greenhouse gas only fingerprint that you would see. And it's something that I think people, even if they didn't know beforehand, the idea that sort of heating up the surface in the lower atmosphere but cooling the stratosphere, I think they can get that wouldn't happen just from the sun. In terms of, there's a wealth of other attribution stuff you can do with optimal fingerprinting techniques and that sort of stuff, but I feel like that's in the weeds.
Great. I have a paleoclimate background and have found that audiences seem to appreciate it when I acknowledge and discuss the more extreme climate has occurred in Earth's history. Have you found the same or differences?
Yeah.
I
get what that's, one of the things that people ask us a lot is they'll say something like, well, the climate's changed before, right? Or like, it was hotter when the dinosaurs were alive, right? Or CO2 has been higher in the past, right? And I think that gets to a very interesting communications / science thing where we can answer those questions very literally, and we can say, yes, it was, about 3 degrees warmer during the Pliocene, which is what I studied, most during my doctorate. And, during the Triassic, it was much, much hotter. But what they're asking when they ask those questions, they're not really asking about those periods. They're saying, if that is true, then why do we need to care now? And I think being able to both, answer those questions, but also understand the question behind the question is a really underutilized skill that we can do more of. And what people need to understand is that, there's two really important things to understand about understanding the climate of the past. Number one, those past climate changes, those things that those people are talking about, are part of the reason why we understand that humans are causing climate change now and how bad it could be if we continue to spew out greenhouse gases. And the other thing that people need to understand, I think, is that we're doing this in a geologically unprecedented way. We are emitting CO2 faster than has been emitted in the past 66 million years, conservatively. So, to understand that it is sort of geologically unprecedented, but that geological stuff actually informs us about why we're, seeing climate change today, and why it matters.
Thank you. Who else at NASA is working on the strategic communications? As a communicator of science, I think that we have so much to gain from integrating these empirical approaches to communications in our normal workflow.
I mean, I think a lot of people are working on this stuff, but this is a kind of like on the science side, there's a lot of different communications teams around. And I think that we're sort of trying to move to a more unified approach, both, in terms of the science side and the comm side. But a lot of people is the answer.
Could you talk more about your comment, There's Hope?
Yeah, that's a great, I didn't necessarily think I would have time to get into some of the other aspects of that, but basically, my message to people is, by studying the climate of the ancient past, and, studying the climate today and looking at climate model projections of the future, how much climate change you see and how bad it gets is sort of this combination of factors. It's, how much we choose to emit, how then the climate system responds to those emissions, and then how life responds to that climate change, or infrastructure would be affected by that climate change, that sort of thing. It's sort of those three pieces combined. And what we've learned, over the last 15, 20 years especially, is that how much the climate changes in response to a given change in what we call radiative forcing, essentially the greenhouse gases. The very best case scenario that it's not going to change much at all, we know that's not true. The climate changes quite a bit when you change something like the amount of CO2 by an appreciable amount. On the plus side, even though those best case scenarios are not feasible, the very, 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 very worst case scenarios that were still maybe within the realm of possibility about how sensitive the climate was to those changes, those also look very unlikely based on the paleoclimate side and also understanding information about climate models in the present. So we've sort of ruled out the best case scenario, ruled out the worst case scenario. The scenarios that are left are very, very serious, but they're we have the ability to do something about them. It's not as though we have passed a point of no return. That's not how this works. The other aspect of why I'm very hopeful is that the climate sensitivity side, I think the very highest stuff seems like it's off the table. The very, I think, underappreciated good news side is that the emissions, the future emissions, trajectory that we're on, we had sort of feared that we were on, the very highest end possible about how much we were emitting. But because there has been such a tremendous advancement in low carbon energy over the past 15, 20 years, we're actually, sort of our where the trajectory we're on now looks a little bit more like the mid-range. That doesn't mean the high-end range is impossible. It just means it's not necessarily the starting point we're at, and that means we can bend it down even further. I think you're muted still.
Right. Curious if you have any advice on how we should be talking to our kids about climate change in a way that's frank and doesn't sugarcoat the problem.
Yeah, I mean, I think the thing, to speak as a parent of kids and not as a NASA employee, I am very much talking to my kids about sort of their role as citizens and their role in shaping the future that they can have and their responsibility to put people in office who take their concerns seriously. And that's a conversation that I did not have with my parents when I was a kid. It's climate change is certainly not the only reason why I'm having that conversation with my kids, but it is a big part of it. And I think, it's great to sort of teach them, behaviors that individually can change, can reduce emissions. But the reality is that if we want as a society to make different decisions about our energy futures, we need to have policy. And if that is true, we need to make sure that the people in charge of those policies understand what we want as citizens. And that's what I'm working with my kids to understand.
If people wanted to dig in on the research behind effectively communicating climate change further, what resources would you recommend?
Yeah, the National Academies has had a long-running colloquium about, the science of science communication. I think they collate, findings every so often. So if you sort of Google the National Academies and then also like the science of science communication, I think probably that should get you somewhere. If that does not work, just if you shoot me an email, I can provide a bunch of resources. I will say if you're looking for just like a quick, easy read, that's not necessarily specific about the science of communicating science, but just sort of practical communication tips. There's a really wonderful book. It's a very fast read. It's called Made to Stick by two guys, they're brothers, last name is Heath, and it's just about how to sort of make memorable ideas. And that Made to Stick book, I find very useful as a starting point about sort of trying to get people to think about how to make messages that resonate.
Thank you. Recently, I've been trying to work on the concept of climate justice, infusing this into my public talks. It is a fact based on science that people who often suffer the most from climate change are the least responsible for causing it. Do you have any thoughts on talking about scientific understanding of climate justice issues while keeping it in our policy relevant, but not policy prescriptive box?
Yeah, I mean, I think that's a great question. I think there is an implication when you say climate justice that there is a policy, sort of either to be done or not done to meet that injustice that you need to be very cognizant of if you're speaking in a capacity as a NASA person. But that is an absolutely true, great point about sort of there is a science aspect of this about the difference between who is emitting and who has historically emitted and who sort of will be on the receiving end of the most dramatic climate changes, especially if we don't, rein in emissions. But, even if we do, that sort of inequality between sort of cause and effect, if you're talking about that in a science-based way, that's a science thing. That's not a politics thing. That's a science thing. If you then go a step further and start to suggest policy remedies in a NASA capacity, I think then you'd probably be over the line. But I mean, we absolutely have gotten that question. How we talk to our science folks and how I answer that question is I am very, upfront about what the actual evidence shows. I think a great point about that is like somebody will say, well, China is now emitting more CO2 than the United States. So they're really the ones at fault. And that sort of, there's a science answer to that, which is that, the amount of CO2 that a country emitted this year, or even the last couple of years isn't what matters. It's the cumulative emissions over time that really matters. And that gives you a very different answer, that then North America is, far and away more responsible, that kind of stuff. Those are science questions that I think get to that point.
Well, thank you so much. We're at the top of the hour. I appreciate your phenomenal talk today. Another virtual round of applause. Thank you so much, everyone, for all the questions. Unfortunately, I'm sorry we couldn't get to them all. I really appreciate everyone joining us today. Happy Earth Day tomorrow to everyone. And please remember that we still have 2 additional talks. We've got one Monday on the 26th and another one on Thursday, the 29th. So we hope to see you all again. And please also do not forget about the headquarters Earth Day events tomorrow as well in the afternoon. So thank you very much again, Dr. Jacobs, and thank you very much, everyone, for joining us. Stay safe, everyone. And I'd like to thank Darlene for pinch hitting for me today as well. Thank you.